Hello, everyone. My name is Deborah Hanus, and today I'm going to talk to you about some things that we can do to use machine learning more responsibly. To start off with, I'll tell you a little bit about myself. I did my undergraduate degree at MIT in computer science and brain and cognitive sciences, and all of my research there focused on developing computational models of how people perceive things. And that was my first introduction to computer science, statistics, and a lot of the things that I ended up using in machine learning. After that, after finishing my bachelor's and my master's at MIT, I spent a year as a Fulbright scholar learning about how education translates into job creation, particularly in the technology sector. Then, when I returned to the United States, I took a job as a software engineer, as an early software engineer at a startup in San Francisco. And then I decided to quit life as I knew it and start a PhD program at Harvard University, where I've been doing a lot of work in machine learning, particularly machine learning applied to medical data. And during my time at Harvard, I interned with the People in AI Research Initiative, which is part of Google Brain, and spends a lot of time thinking about how to make machine learning more fair, more interpretable, and more useful to everyone. And then, just recently, I started a leave of absence from my PhD to start a machine learning related company. So, as you all might have heard, machine learning is the future. AI is very exciting, and it's made a lot of progress in the last few years. It's responsible for all sorts of advances in computer vision, speech recognition. It's works well. It has given us great models of human behavior and computer vision, and even self-driving cars. So this is a soap dispenser, and you can see that someone with light skin puts their hand under the soap dispenser, and it dispenses soap. But when someone with dark skin puts their hand underneath it, it doesn't recognize that that's a hand, despite the fact that the people who designed this had every intention of designing a soap dispenser that responds to hands. Instead, they designed something that seems to respond to light things appearing beneath it, whether it be a light hand or a light paper towel. So, despite the fact that machine learning and artificial intelligence is responsible for a lot of really amazing advances, we still sort of have to ask ourselves, why is it that sometimes artificial intelligence is so unintelligent? So to start off with, we'll step back and talk about some of what goes into this process of machine learning. I'd say machine learning is sort of this mixture of probability and statistics, linear algebra, and computer science that we use to fit models and to make sense of large amounts of data. And this is a particularly amazing time to be working with Python in machine learning because there are all sorts of amazing tools that make it possible for software developers to make some really awesome machine learning products without necessarily needing to know all of the details of what's happening in the machine learning. One example of this is scikit-learn, which has some amazing machine learning models and documentation that you can get going with relatively quickly. Theano and PyTorch are fantastic for writing research-grade code where you want to do something pretty cool, but that it'll probably get thrown away in the end. Whereas TensorFlow adds some robustness so that you can do this with a distributed system and larger amounts of data. And Keras is a really nice wrapper around these tools like Theano and TensorFlow, which enables you to do some great things with deep learning without necessarily having to understand what every parameter in your neural network is doing. But this introduces us to a whole new type of debugging. Instead of just saying, why isn't my variable defined, suddenly you go through code which looks perfect, but can't get your algorithm to converge. Why doesn't it stop running? And so then you go through this, for some extended period of time, and then you find it converged, you're done, it even has 90% accuracy, and you can push it to production, but this is where we need to exercise some caution. because machine learning is all about data. And if we aren't feeding our machine learning algorithm good data and we don't understand what the data is doing, we similarly are not going to be able to design systems that do what we want to do. So some examples of machine learning going a little bit awry because people did not understand what the data was that was going into it is there's this MIT graduate student, Joy, who spent a lot of her master's thesis working with facial detection software. But she could never test her own software because it would never recognize her face. So in order to start testing her software, she had to start wearing this mask, this white mask, which really looks absolutely nothing like a face. And the reason for this is a lot of facial detection software is trained on data sets that look like this, where there are many light faces. So what the algorithm is learning, what they wanted an algorithm to do is to design something to recognize faces, but instead they found that they designed an algorithm to recognize something with eyes, nose, a mouth, and light skin. Another example of this is something that I think both Christine and Lorena touched on, which is predicting recidivism, or if you or I were to commit a crime, this predicts how likely it is that we would be likely to commit more crimes. In the United States, we have, unfortunately, a large problem with prisons being overcrowded. So if someone was having a bad day and they made a mistake, and they're never going to commit a crime again, we'd like to get them in and out of the jail system as quickly as possible. But if someone is going to keep committing crimes, it's possible that they should stay in jail a little bit longer. So this was the idea behind making this test for incoming criminals. So we can look at some of these examples. One is an example of Brescia and Vernon. Brescia was an 18-year-old student who was running late to pick up her sister, and she saw an unlocked scooter. So she picked up the scooter and started scooting down the street with it. Someone stopped her and said, "That belongs to my son," and she dropped the scooter and went on. But it was too late. Someone had called the police, and so she was charged with petty theft worth about $80. Separately, Vernon was caught shoplifting some items which were worth $80. But if you look at their histories are actually quite a bit different. Brescia had a couple minor juvenile offenses, whereas Vernon had 2 armed robberies. He had, and 1 attempted armed robbery. So it seems like he's really going out of his way to plan these robberies. But yet somehow he was predicted as low risk, someone who probably wouldn't offend again. And Brescia, who was just running late to pick up her sister, was predicted as high risk. Another example of this is Dylan and Bernard, where they both had minor drug offenses. They had some drugs on them. And this resulted in Dylan being marked as low risk and Bernard being marked as high risk, despite the fact that Bernard had almost no record. He once resisted arrest, despite the fact that he wasn't charged with anything else. And he never committed any crimes after that, whereas Dylan continued to have more drug possessions. And the problem with this algorithm is we thought, or the people who designed it thought that what they were getting at is they were getting at the likelihood of someone of someone committing more crimes, but in fact, they were asking the wrong questions to figure out the answer to that. They asked questions like, do you know anyone who has committed a crime? Has anyone in your family committed a crime? And the end result of this is, if any of you are familiar with the neighborhood structure in the United States, often minorities tend to live in certain neighborhoods, and these tend to be poorer neighborhoods, which do tend to have more crime. And so when you live in a poorer neighborhood, you have lower income, it is much more likely that you know more people who have committed a crime just because they're in a more desperate situation. And that doesn't mean that you yourself actually would ever commit a crime. So this is an example of how, in addition to designing a brilliant algorithm, you also need to think really carefully about the behavioral consequences of the data that you're collecting and how you collect that data. So this is a good place to stop and just remind everyone that when you're doing machine learning, you should remember that the machine has no brain. So you need to do some of the thinking for your machine learning model. I know people always like to think about this scenario in which machine learning builds AI, in which we have these AIs that are like a Terminator, and we have this human-like intelligence. But I prefer to think of the things that we can build with machine learning as more like a seeing eye dog, or another animal that can be really helpful. If a seeing eye dog on its own is not that much different than a stray dog, but if you train it and you think about what it is you want to do and you do a good job explaining what it is you want it to do, the seeing eye dog can make it possible for people to do things that they never would have thought possible, and they can also do things that we never would have thought possible in order to help people. So in this talk, we're going to talk about how we can do a better job training our algorithms to be more thoughtful and to make better decisions in the realm of artificial intelligence. So, as we just discussed, your results are really only as good as your data in the machine learning, so we need to do some of this thinking ourselves. So, what are some ways that we can try to improve our machine learning models? One is we can make sure that we explore and really understand our data. Next, we can make sure that after our algorithm has converged and we have some sort of accurate model, that we explore those errors and see if there are any systematic errors that it's making. And then finally, we think about interpretability to make sure that we know that our algorithms are doing what we expect them to do. So, step one is exploring and understanding your data. And to do this, we'll just take a step back and think about some of the places that we can get data. Often we can get data from these curated data sets that we get from websites like Kaggle or the US Census. Often these are relatively clean data sets that are already somewhat structured, and people have already thought of at least a few problems that you can answer with them. There are also these semi-curated APIs like Twitter API, which gives you access to a lot of tweets, or the IMDb Pi API, which gives you access to a subset of IMDb. And then my background is in machine learning applied to medical data, and so in this case, you might also have careful cooperators. In this case, I know things about machine learning, but I really don't know that much about medicine. And so in order to understand how the medical data was collected, I need to spend some time working with doctors and making sure that I understand make sure that I understand the way that they recorded the data and some of the things that might influence it. And another way we can get data is just web scraping or getting data off of the internet. But we have to be careful with all of these data sets because lots of times they have information in them that we wouldn't necessarily expect. And that this data can often express human bias because really we as humans are the people who produce all of the photographs on the internet, all of the text on the internet, and everything else. So an example of this is this data set that comes out of UMass Amherst that's been used in a lot of research called Labeled Faces in the Wild. So this was made by scraping websites and looking at photos of mostly famous people found on the internet. So here we can see a number of photos, and there are 12 photos of Harrison Ford, 12 of Michael Jackson. But some people were more photographed than others, and there were many photos in the data set. And one of these was George W. Bush. And this makes a lot of sense. I believe this data set was created at the time that George W. Bush was the United States president. He's the president of a large, wealthy country. He comes from a wealthy family and has a very storied political background. But one thing to think about here is this is how a lot of photos are taken. Like, celebrities tend to have certain connections and come from a certain background. And if we tend to take more photos of wealthy, powerful people, and wealthy, powerful people tend to be white or well-connected or any of these other things, we might, and then we train our algorithms using this data, we might find that we create a new norm, which is being like people who are wealthy, white, powerful, wear suits, and are presidents of massive wealthy nations. So this is one way that we can think about this. Another example of this uses word embeddings. So word embeddings are a method of representing words and text on the internet as vectors. And once you represent the words as a vector, you can then plot it in space, like you can see here. So you might make a transformation to these words, like on the left we have walking and swimming. And we make the same transformation to both of those, and they become walked and swam. And similarly, on the right we make a transition between male and female. So if a man is a king, a queen is a woman is a queen. And these are all sort of things that we expect. But Word2Vect is this group of models that's used to produce these word embeddings using text off of the internet. And recently, a group at Boston University explored these word embeddings, and they found that when you plot the words this way, if you compare man is to computer programmer, and then you subtract off the man vector and add a woman vector, the representation is the same as homemaker. So for some reason, using this data from the internet with all of these biases, it seems that the internet thinks that the equivalent of a programmer for a man is a homemaker for a woman. So this paper is a nice place to start when thinking about how to debias some of the text so that you don't introduce these same biases into your own models. Okay, so we've talked a little bit about some of the things that can go wrong when you use data on the internet, and some of the ways that you can explore that. And so the next step is making sure that we really understand our data. And we understand what is there in our data. And this is a tool which came out of the group that I worked in at Google Brain last summer that helps you to explore your data. It's essentially a Jupyter notebook which takes all of your numerical variables. So in this case, and a good example is age. Age is a continuous variable which goes from 0 to not infinity, but it's continuous to some large point in the future. And you can look at, and so you can explore your data set looking at both your training and your test set and say, make sure that there's a similar distribution of ages in both your training and your test set. You don't want to, so that you can avoid overfitting to your algorithm or potentially using data that is too different in order to train your algorithm. So this is notably, before we even start machine learning, this is just going to help us understand our data sets so that we can start to see things that our algorithm might be learning. And then on the right, it also does something similar with categorical features, like what country are you from? So we can look at a general distribution of how many people are from a given country. So this can be really helpful in just helping us understand what data is going into our algorithm. But it's possible that it doesn't have everything that you need. Sometimes for specialized data sets, you want to look at things in a specialized format. So you can also sort of use other tools or to some extent roll your own tools using things like Tableau or Plotly, Bokeh in Python, D3.js or Matplotlib, all great visualization tools that you can use to make sure that you look at the distribution of variables of what is going into your algorithm. Okay, so we've talked about exploring our data and making sure that we know what is in our data. But now we also need to talk about how we can understand our data. So, like I said, I've done a lot of work with machine learning applied to medical data, and this is a particular example of how you really need communication to train your machine learning algorithms to do what you expect. So when I started my PhD, I would say I knew a good amount about machine learning, but I didn't know anything about medicine. So it's very easy, if you just apply machine learning to a data set without understanding how it was collected, you can draw some pretty weird results. So an example of this is, let's say we're looking at patient vital signs, like heart rate, how much oxygen they have in their blood, blood pressure. And the oxygenation level of your blood is measured using this oximeter, like you see in the picture. So let's say we look at this data, and we see most of the oxygen levels are pretty high. They're like around 98, 100%, right where we would expect. But periodically, it's dropping down to about 60%. So what could be going on here? I mean, one idea is maybe this means that the patient is just holding their breath for a really long time. Is the patient having a heart attack? Like, what could be causing their oxygen level to go down so quickly like this and then spike back up? But then, what if I told you that a white hospital sheet has 62% oxygenation? Then suddenly this actually makes a lot of sense, because it's a lot of trouble to turn an oximeter machine on and off. So if you're busy and you're measuring the vital signs of a lot of patients, you're not going to turn it off, you're just going to take it off their finger and throw it on the hospital sheet. So now we know that we probably shouldn't be paying attention to this data because we aren't measuring a human's oxygen level right here, we're measuring a bed sheet. Another example of this that we run into sometimes are things like electronic health records. When you go into the doctor, they take some doctor's notes, and maybe they say that you're sick with the flu, so there will be a diagnosis code for the flu. Or if you have diabetes, there will be a diagnosis code for diabetes. So let's say we want to find how long a patient has diabetes. So one way that we might consider doing this is just looking at the diagnosis code. When were they first diagnosed with diabetes? This seems like a very easy approach. But if you know anything about health insurance in the United States, which I really hope you don't, you'll know that they actually, in order for insurance to cover a test to see if you have diabetes, they need to diagnose you with diabetes. So first you need a diagnosis code for diabetes to learn whether or not you have diabetes. So lots of people who do not have diabetes have the diagnosis code in their records. So it seems like this might not be a good way of doing this. Another way you can do this is you can compare to a control. You can say, maybe I want to know if this person has diabetes, so I'll compare them to this other person who I think doesn't have diabetes. But then you have to deal with this fact. What if that people are different? The normal blood sugar range is an average. It's not the same normal for everyone. So if you compare these two people, they might have very different genetics, they might have a different family history, and it might not be great to compare the two of them in order to get a result. Another way you can do this is you can define some sort of rule. Like maybe we say if someone has had more than 3 diabetes treatments over 12 months, then we say if they've had that many treatments, they probably have diabetes. And this is important because you can also have things like gestational diabetes, which means that when a woman becomes pregnant, she has diabetes, but only for the amount of time that she's pregnant, and it goes away when she has the child. So even if we had defined a rule that was 3 diabetes treatments in 6 months, that still wouldn't have worked. So in general, we have this problem that I think people in a lot of fields have, which is there's often this gap between the people who do the data collection and the people who do the data analysis. And the only way that we can bridge that gap is with communication. So we go out and we find the people who collected our data and make sure that we understand where it's coming from. So from my perspective as a researcher, there are some ways to get domain knowledge. One is I can become a medical professional. I can go to medical school and then be a doctor and also do machine learning on the side. I really don't want to spend another 6 years in school, so I'm not going to do that. Alternatively, I can just find a great collaborator, like a doctor or a nurse, and they can tell me how they collect the data. And if I find something that I think is interesting, I can run it past them, and I can say, does this make sense to you? And they have the domain knowledge to be able to have a lot of insights that I wouldn't be able to have just because they were the ones who really collected the data. And similarly, if you work in software, this is also an issue. Often, when you start a company, you have software engineers who know how to build products, and they know that they should be collecting data because data is important and machine learning is the future. But they might not know what questions a data scientist would want to ask. And so some ways that they can do this is you can have a data scientist early and make sure that the data scientist collects all of their own data so that they know, so that they're storing it in a way that makes sense for them. Or you can have them collaborate closely with the engineers so that they understand what data is being stored, and the engineers can make sure that they store the data that the data scientists need. All right, so we've gotten through a lot of this so far. We've talked about exploring and understanding our data. And now we're going to talk about potentially exploring our errors. So we're talking about that point where our algorithm has finally converged. We think we're done. Maybe we have 90% accuracy. And we just want to be done with this at this point. But we want to know if our machine learning algorithm is doing things we don't expect. So we're going to ask, what did our model misclassify? And are any of those errors systematic? One relatively standard way of doing this is using a confusion matrix, which if you've taken an introductory statistics class might look uncomfortably familiar. So let's say we have an example. We work at a company like YouTube. And we want to determine whether our content is sensitive content, which parents might not want their children to see because there are some dark corners of the internet that you do not want your 13-year-old to venture into. Or whether this is safe content, which is going to be informative and useful for everyone. So if we label content as sensitive, and it actually is sensitive, that's going to be a true positive. If we label data as fine, and it is fine, that will be a true negative. If we say that data is sensitive, but it is not sensitive, it's fine, that would be a false positive. And if we say that the data, and if we leave sensitive data unmarked, and it still is left out in the open, that would be a false negative. So when people are approaching the problem of bias, there are different ways of approaching this. Sometimes people might say, we want equal amounts of error. Maybe we want similar numbers of false positives as we want false negatives. Another way that people can think about this is they might say, look at the absolute worst case scenario if they make one of these errors. So in the case of a false positive, we're saying there is content, which is fine, but we're saying that this is sensitive content and we're not going to let children access it. Whereas in a false negative, we're saying this is data that is sensitive. It could totally traumatize a child if they saw it, but we're going to leave it out there unblocked. So which do you think is worse? Sometimes some people might think the false negative might be worse. And I think that it's possible that that's what the people at YouTube thought when they tried labeling their sensitive content about a year ago. But the end result was there was a pretty bad outcome on the other side, which was because there were so it turned out that the false positives also turned out to be very bad because a lot of lesbian, gay, bi, and transsexual students go to YouTube for information, for community, so that they know that someone else is out there that they can work with. They go there for friendship, and they go there to get health information, to take care of themselves. They go there to learn how to stand up to bullying. But somehow YouTube had blocked many of these videos that had any sort of LGBTQ content. So there was a large outcry, and there was a lot of negative publicity for YouTube. So it's worth thinking about what the absolute worst outcome is in either case, and defining where you might want errors in either case, and define your model such that you avoid the absolute worst possible outcome. And we went through this with a binary outcome. Is something sensitive or is it not? But you can also do this for multiple classes. So this is just an example using object classification. So it shows, so if you are classifying a car as a car, that's great. But if you're classifying a car as a couch, that's something that you can see here in your data set pretty easily, and you can explore why are your cars being classified as couches, and you can look more carefully at your data set. Something like this could also do something to, could also have an impact in detecting discrimination, like if you have an algorithm that doesn't recognize dark skin tones or isn't acknowledging someone from a certain racial class. All right, so we talked about exploring and understanding our data. We talked about exploring our errors. So now let's talk about how we can make results more interpretable. So both Christine and Lorena have touched a little bit on interpretability, but in the research community, there are actually a lot of different ways of thinking about interpretability. And we all need to be thinking about this to some extent because the EU recently passed a general data protection regulation which acknowledges that right now machine learning models are affecting what news we see, they're affecting what events we see, to some extent even who we spend time with. So, and in some cases they're even predicting how long we're going to stay in jail. So what this regulation says is if an algorithm has said something about us using our data, we can ask for an explanation and ask why it made that decision. But, so this is a form of interpretability, but we should think about what sort of answer we would want in response to this question. Sort of two main ways that people often talk about interpretability in the research community is first the interpretability of machine learning models. So like deep learning algorithms and neural networks are known for not necessarily being very interpretable because there are a lot of parameters defining how much noise you have, the parameters change from layer to layer. You don't necessarily know what every layer is doing. And then there's also interpretability of results, which we'll talk more about in a couple of minutes. So first, let's talk about this interpretability of machine learning models. There was this great example of this I think it was last summer, where Facebook AI research was trying to build two chatbots to negotiate with one another. So they defined all of these terms and probably used some sort of reinforcement learning algorithm to get these chatbots to learn to speak to one another and to come to good negotiations. And the goal for this was that they would be able to communicate with people. However, they had mixed success. The chatbots did indeed learn how to negotiate, but they made up an entirely new language that humans couldn't understand. So because there were these aspects of this that they didn't understand, they couldn't define what they wanted the algorithm to do. And they ended up designing chatbots that don't speak English. So one sort of state-of-the-art way of managing this right now is this tool called LIME. And this stands for Local Interpretable Model Agnostic Explanations. And what this does is, in this case, what it's trying to do is we have this image of a tree frog holding a heart. And it splits it up into lots of little sections, and it says, which one of these sections of the image is most responsible for us interpreting this as a frog? So it looks at each of these little pieces of the image and compares it to other images. And on the right, you can see that it seems like the most interpretable part of the image, the part of the image that tells us that this is a tree frog, is the tree frog's mouth. Even though there are other parts of the image that look a little bit like the tree frog, like the red spot on the hot air balloon or the pool cue balls. So that talked about the making sure that the parameters of our machine learning model are interpretable. But if we think back to the EU regulation, it's worth asking ourselves, is that really the kind of explanation that we want? Like, if an algorithm has told me that I need to stay in jail longer than someone else, do I really want to hear the answer, well, your gradient moved a little bit to the left and his gradient moved a little bit to the right? Like, that doesn't make any sense. So I think when we're building machine learning models, it's really helpful to think about how we can build models that people want to use, that are good for assistive technologies. An example of this is something like that you use every day is your cell phone. When you're texting, there's this autocomplete. And you might not know everything about every machine learning model that is predicting what your next word is, but you have this general idea that if you say something like, what is your, it's going to say, think that life maybe is a good completion of that. But this is really notable because not only is it using a machine learning model to predict what you might want to do next, letting you type faster, it also leaves the decision in your hands. If it's given you 3 bad suggestions, you can just use none of them and continue on without the help that the machine learning model was trying to give you. This also sometimes comes up in the medical context. A really great example of this that I think of as an amazing assistive technology for medicine is something that helps doctors with prescriptions. So all this does, it uses no machine learning. It just knows the rules for the appropriate ranges for a prescription. And often there's a problem that doctors are really tired, they have horrible handwriting, and when they write out a prescription, they might write out a prescription for 10 times the amount that they're actually supposed to. You can imagine this has horrible health effects. So it would be really helpful if instead they had a tool to help them with this. And all this does is they write out the amount that they expect the prescription to be for, and then it asks them, did you mean to prescribe 10 times the normal amount? And if they say yes, it leaves the choice in their hands. They actually did manage to want to write that prescription. But it also keeps them from making mistakes that they might have otherwise made. And as such, it saves a lot of lives. This is a figure from a paper written by Finelli, Doshi, and Bean Kim, which tries to further assess how we can research interpretability and define what these different meanings of interpretability could mean. One of the main ideas to take from this is if you have something that you're expecting to do a human-like task, you should compare it to how well a human does it. If you want something to interact with a human, you should make sure that humans actually understand it. So, to summarize, a few concrete steps in order to use machine learning more effectively are make sure that you can explore and understand your data. After you understand what is going on in your data, make sure that you make time to analyze your errors, and make sure and think about how to make your results interpretable, and design products that return results that you would actually want to see yourself so that you can trust your algorithm. Otherwise, because this is the only way that we're going to actually make both people and machine learning more effective. And finally, if you don't know something about your data, find someone who does, because that's the only way that we're going to make artificial intelligence as intelligent as we want. Thank you.
Hi, thanks for the talk. Just found the use of machine learning for medicine really interesting. Can you comment a bit more about your research and what sort of stuff are you doing in the related to medicine?
So the question was what sort of research I've done? So my undergraduate research was all developing computational models of how people perceive things. Particularly like if you walk into a room, technically you see everything in the room, but you can't attend to everything in the room. So you can actually develop a mathematical model of which things you're most likely to be able to attend to develop a model of how human perception might work. That's what I did my undergraduate research in, and then more recently I've been doing machine learning applied to medical data. And I've worked on two main projects. One was using reinforcement learning to predict effective HIV treatments. So one common way of treating HIV is you give someone some drugs which knock out both the HIV and everything else. So people are actually usually feel worse when they're taking the drugs, but you can sort of cycle these on and off, and it sort of becomes a control problem, a lot like robotics. How much of a given drug do I give someone on a given day? And so you can use reinforcement learning to optimize this function of having the most good things in your blood as opposed to bad things. And the other project that I spent some time working on used data from medical forums. So there are a lot of forums centered around a certain disease like autism or depression. So people use usually some anonymous handle, and they write about their experience with the medications, how long they've been sick, if they had any symptoms with the medications. So there are a lot of things that you can do to get a better idea of what medications work for who using those forum posts, and that was my second project.
Hi, so also thank you for the talk. So with regards to medical data, it's well known that there's a lot of unstructured data in terms of medical histories, pathology reports, radiology, etc. So what's been your experience extracting useful information from those reports, knowing how disorganized it is? Like for example, automated extraction via unsupervised learning and such techniques.
Yeah, I'd say that is a very hard problem. You can start usually with a lot of structured things though as well. Like even if there are lots of doctor's notes, you can start with things like diagnosis codes, the dates that people were diagnosed, and you can actually get a lot of useful information from things like that. But in general, there's sort of a whole research area centered around making this very unstructured data a little bit more structured so that you can do useful things with it. And another whole research field dealing with things like missing data. There are also all the people who didn't come to the hospital. And why didn't they come to the hospital? Maybe it was because they were well, or maybe it was because they chose an insurance policy that makes it too expensive for them to come to the hospital. So there are a lot of issues with structured data and figuring out how to use that data appropriately, and most of those are still open research problems.
So I have a question about, you mentioned that you need to understand the data and then try to fix the biases, right? Now assume you have built something, some machine learning algorithm which works almost perfectly for 99% of the population and doesn't work at all for 1% of the population. And it's a specific population. You could have designed Siri, which works 99% of the population, and for 1% of Indians, it doesn't work at all. So that's one choice. The other choice is that you remove the bias from the data and make it work 95% of the time for the entire population, so there is no bias. So in one case, you have a better model, 99% accuracy. In the other one, you have an inferior model with 95% accuracy, which, like from an ethical standpoint, what are people thinking is a better choice? An inferior model. And then you can push this argument further. So 95% and 99%, you may think that, oh yeah, I'll deal with 95%, that's fine. What if to accommodate that 1%, suppose the error rate is pushed to 80%, or not error rate, the accuracy is pushed back to 80%. So do you accept an inferior algorithm in favor of inferior and fair algorithm as opposed to a biased but superior algorithm?
So I think it still is really important that we analyze our errors and we look at what the algorithm is getting wrong, because we might have a model that predicts with 99% accuracy that a population does not have a rare form of cancer. And it can get that accuracy just by always saying, no, this person does not have cancer. But it's incorrect for 1% of the population, and that's a very important 1%, which is the 1% that has cancer. So I think if you have a model that works very well for 99% of the population, but not 1% of the population, you need to understand why, otherwise you don't have a very good model. And from an ethical standpoint, I agree, if you actually want to trade off a better model for well, first of all, I would challenge the point that accuracy might not actually be the metric that we should be using to determine whether a model is good or bad. It's possible that we should be looking at who it isn't working for and then modifying the model in order to make it work better. But that said, I would say all of fairness is still a very open research problem, and we don't know what's right. I think the most important thing right now for us is to watch the research as it's coming out so that we have a better idea of what we can do for our algorithms, but also just be aware that this is a problem. Because if we have more smart thinking people who are good programmers thinking about this, it's much more likely that we're going to develop a good solution. So I would just, as you're building your machine learning models, think about how it is you can analyze those errors and make them more fair, and how we can get this idea out to more people. Maybe all of our machine learning tutorials should be followed up with another tutorial about analyzing your errors and making sure that you understand why it has certain errors. And maybe that should become a part of our basic machine learning education. So I would say there might not be an obvious good answer there, but we should definitely all be thinking about it.
Hi, I have a question about for the model design. How do you select the algorithms for applicate in medical data? Because for me, it's very hard to select algorithm, and I can implement the best algorithm and have grown errors in the output data.
If I can repeat the question was, how do you choose an algorithm for your data? Have you ever seen the sklearn visualization for this? I think it was actually developed as a little bit of a joke for some basic heuristics, but if you're just getting started with machine learning, it's actually amazing. It is an image. This is what I'm talking about. So it's just a flow chart. It asks you all these questions like, what do you want to do? How much data do you have? Are you trying to do a classification, or do you want a clustering at the other end? And this is really helpful, if nothing else, as a starting point to figure out some of the things that you could do. And then once you get into one of these, you can learn more about it and start to do, and then you can select an algorithm based on what minimizes your error eventually once you get started in the right direction.
The last question.
Hello, I heard you say a little bit about how algorithms are saying with who we should spend time with, what should we read, and that it determines a lot of our daily life. And I've read about a little bit about how we're changing from humanism to dataism. And I ask you personally, do you think that machine learning and artificial intelligence is ever going to be the end of free will as we know it? I mean, we're not going anymore to the bookshop and reading the description of a book and probably picking a crappy book, but that's what I chose, right? We're going to, I don't know, Goodreads or something like that, and we see what it recommends, and we choose it based on algorithms. So how do you think that it's impacting our free will?
I'm sorry, can you repeat the question?
How do you think artificial intelligence is ending? I mean, do you think artificial intelligence is ending our free will?
Do I think artificial intelligence is going to get better than programming or programmers?
No.
Or,
Like, what do we choose? Like, yes. Like, we make decisions every day, right?
yes.
And we choose this book and we choose this movie, right?
Mm-hmm.
And sometimes you go to Netflix and you watch a movie based on an algorithm that suggests that movie, right?
Yeah.
Completely opposite to when you went to Blockbuster and you just walk and pick a movie and
Yeah.
it was your movie, the one you chose. So at the beginning, you said a little bit about how algorithms were defining what we do.
Mm-hmm.
So do you think that in some point we are only going to listen to algorithms because algorithms are going to be much better than our own thoughts? I mean, at least in that kind of stuff. I mean, they're going to know us way better than we know ourselves.
I really hope not. So to repeat the question, she says, right now we do have algorithms that are telling us a lot about what movies we should watch, what books we should read, what things we should buy. At some point, will these algorithms learn more about us than we know about ourselves, and so we don't have to make decisions anymore? I think to some extent this is a generational divide. To me, that sounds horrible. I want to make all of my own decisions. I spoke with my 15-year-old brother the other day, and he's like, I love it when ads track me because it means that they give me things that I want to buy. So I think that one very important thing that we can do to improve our educational system is to make sure that we still are thinking about the ethics behind all of these, making all of these recommendations and making sure that we can think it by ourselves without the algorithms, because otherwise I think, like I said, these machine learning algorithms, they really are not that smart if you don't do some of the thinking for them. So I think it's important that we continue to have our ability to think so that we can train the algorithms effectively and we can both be more effective.